Hello, my name's Ben Holcomb. I'm an associate professor here in the School of Mechanical and Mechatronic Engineering in the Faculty of Engineering and IT at UTS. And I'm here in the Dynamics Laboratory, which is an incredible facility we have in the basement of Building 11 here. And I'm here to talk to you briefly about our half-car rig simulation experimental setup that we have here. This setup is a simulation of a multiple degree of freedom system. We have 4 degrees of freedom with this system. Here, this blue frame is what we refer to as the sprung mass. This is representative of the body of the vehicle. And then these 2 green frames sitting below here and here are 2 unsprung masses. This sprung mass has a mass and, of course, an inertia. It can translate up and down, as well as rotate about the central location here with this bearing. These 2 unsprung masses are connected to the sprung mass by some springs and dampers, which are representative of the suspension system of the vehicle. And we have them connected via some very stiff springs with shorter undeformed length and coil thickness to ground. They're representative of the car tyres. This is an attempt to linearize a car system, a half-car system. Of course, there are also some non-linearities still that persist with this kind of a system. Given that I know the frequencies of the two roll and bounce modes, I can introduce some harmonic excitation to tune those 2 vibrations independently. So here you can see the roll mode, and if I drive this at a lower frequency, I can excite the bounce mode pretty much independently from one another. We can excite all 4 modes for this 4 degree of freedom system by actually displacing this sprung mass from rest and releasing it, and all 4 of these dynamic frequencies will be excited simultaneously. To do that, I can lower the crane here. I can close the clips. I'll just put the pendant here slightly out of the way. Actually, I'll just lift this one back up, sorry. So I'm lifting it up until the rubber pads underneath here are not in contact, just not in contact with the sprung, with the frame, between the frame and the sprung mass. So just put the pendant out of the way. Hopefully that won't fall off. I have to go around and use some quick electronics around here to release this from rest. 3, 2, 1, drop. And you can see that my non-zero initial condition for the displacement of the sprung mass allowed this to fall from rest, and we excited primarily the bounce mode, but all 4 of those mode shapes, those different vibration frequencies will have been excited simultaneously. And we can measure those vibrations using the instrumentation that's fitted to the system. So we have 2 long stroke LVDTs sitting one either side on the 2 springs for the sprung mass here. They've got 50mm stroke. And I simultaneously have, or similarly have, 2 shorter stroke LVDTs connected to the unsprung masses. And hopefully you're zoomed in now and you can see the rod of this LVDT, which is what is measuring the displacement. And to confirm the sensitivity of this LVDT, I can insert a known thickness puck underneath here. And on the acquisition system, which we'll show in a separate video, I will see 2 different voltages, and that allows me to get displacement or volts per millimeter sensitivity value, or millimeters per volt sensitivity value, which we need in the software to convert from volts to engineering units. What I'm interested to do in this experiment is use those measurements and make configuration changes to this system by adding masses, potentially masses to these outriggers here to change the sprung mass and the rotational inertia of the sprung mass, as well as by applying hydraulic pressure using this hydraulic cylinder here to change the spring stiffness and damping that is included in the system via this hydraulic circuit, which is connected to the sprung mass. And so by making configuration changes, we can isolate the various different mathematical descriptions of, for example, the mass and the stiffnesses of the springs, the inherent damping that exists just with the system without the addition of a known amount of extra pressure here, and build up a series of equations where we have some unknowns and some knowns, and by measuring the resonant frequencies, and comparing and contrasting those with the frequencies that we would predict from our mathematical model, we can determine the dynamic characteristics of this kind of a 4 degree of freedom system. That's the end of the video. I hope that was useful. Thank you.